Welcome back to the Deep Dive, Curious Learners. Get ready, because today we are talking about something that sounds, well, like it's straight out of science fiction. Scientists think they may have found the mathematical blueprint for a real portal to the fifth dimension.
And it's not just for fun. This could be the key to solving one of the biggest mysteries in, well, all of physics.
Exactly. So our mission in this deep dive is to go past the headlines. We've got the research. It was published in the European Physical Journal C, and we are going to unpack the specific mechanism here.
Right.
How a warped fifth dimension could solve not just the dark matter problem, but also a huge glaring hole in the standard model of physics.
And it's so important to frame it that way. The stakes are just incredibly high. Dark matter isn't some tiny detail.
No.
It dictates how the entire cosmos is structured, but we've never ever seen it. We're looking for the universe's invisible backbone.
Before we get to that invisible backbone, a quick reminder to you, our listeners, if you're enjoying this, please go ahead and hit that like button and subscribe.
It really does help.
It does. And check out the affiliate links below, plus our fourth wall merch. And of course, let us know in the comments what we should dive into next.
Yeah, we love the suggestions.
Okay, let's unpack this.
Let's do it.
So, starting with the absolute basics, what is dark matter?
Well, it's basically the universe's ultimate pinch hitter. It makes up something like 75% of all the matter in the universe.
75%. That's just a staggering number.
It is. And when astrophysicists look out at, say, a galaxy, they see it spinning way too fast.
Right.
Based on the stars and gas we can see, it should just fly apart. So dark matter is this extra gravitational glue that has to be there to hold it all together.
But we have zero direct evidence for it. It's just a placeholder for mass we know has to exist.
Precisely. Without it, the universe as we see it would just dissolve. It wouldn't work.
And that's the paradox, isn't it? It makes up most of everything, but it seems to just sail right through all the normal matter, the stuff we're made of.
No nudge, no interaction. It's totally invisible and untouchable, which is why scientists are pretty convinced it must have properties that are just fundamentally different from our reality.
Which leads us right to the problem with our current rulebook, the standard model of physics.
Exactly. The standard model, or SM, is amazing. It describes almost everything we know about particles and forces, but it has these two gigantic failures this new research tries to fix.
Okay, so failure number one is the obvious one, dark matter itself.
Right. The standard model has, and I'm quoting here, no viable dark matter candidate. Nothing in the model fits the description.
So if dark matter exists, and we're pretty sure it does, then by definition we need new physics, something beyond the standard model.
Yes, but then there's the second failure. And this one is, maybe even more fundamental. It's called the hierarchy problem.
And this is where the fifth dimension really starts to become less of a wild idea and more of a necessity.
It really is. The hierarchy problem isn't about missing stuff. It's about a math problem, a huge one. It asks, why is the Higgs boson
The particle that gives everything else mass.
That's the one. Why is it so incredibly light compared to the characteristic scale of gravity?
And when you say incredibly light, what's the scale of the mismatch here?
We're talking a discrepancy of 10 to the power 32. It's a 1 with 32 zeros after it.
Wow.
To make the math work in the standard model, physicists have to do this thing called fine-tuning, where they basically cancel out huge numbers with ridiculous precision.
It sounds like a fudge factor.
It kind of is. It's like needing 32 decimal places of accuracy just to explain why a particle weighs what it does. That kind of coincidence just screams that we're missing something fundamental about the universe's structure.
So the standard model isn't just incomplete, it's mathematically fragile.
That's a great way to put it. And because it fails on both counts, no dark matter, and this gaping structural hole, we're almost forced to look beyond our 4 dimensions for an answer.
We need a bigger box to play in.
We do. And that brings us to this new idea, the warped extra dimension model, or WED for short.
Which sounds like something from a movie, but you mentioned this isn't a totally new idea, is it?
No, not at all. The idea of extra dimensions has been around for about a century. But this specific warped geometry was made popular back in 1999.
So what's new here? What did this latest research actually contribute?
Synthesis. This is the first time anyone has used the WED model to cohesively solve both the dark matter problem and the hierarchy problem at the same time, with one elegant mechanism.
Okay, here's where it gets really interesting. How does it work? How does warping a dimension fix that that 32-digit math problem.
So try to think of it less like a parallel universe and more like a big sheet of paper that's been folded or curved really intensely. That's the warping.
Okay.
Our four-dimensional universe, everything we see and know, exists on what's called a brane. Think of it as just the surface of that paper.
So we're living on the edge.
In a manner of speaking, yes. The key is that gravity can travel across the whole five-dimensional space, the whole sheet of paper, but other forces, like electromagnetism, are stuck on our 4D brane.
Okay. So the reason the Higgs seems so light to us is because the warping is what? It's diluting the full strength of gravity on our little slice of reality.
You got it. The geometry itself naturally produces the lighter mass for the Higgs. Without any of that messy fine-tuning, the warping does the work.
That alone seems like a huge win.
It would be. But the theory goes further and uses that exact same structure to explain dark matter.
So how does dark matter fit in? The study focused on something called fermion masses, right?
Yes, fermions are the building blocks of matter. Quarks, electrons, all that stuff.
The things we're made of.
Exactly. And the hypothesis is that these fermions can be communicated into the fifth dimension through what they call portals.
Now, portals sounds a bit dramatic.
It does. Think of them less like a swirling vortex and more like specific quantum connection points, places where our 4D space is linked to the 5D space.
Okay, but hang on. If the basic particles we're made of can just jump dimensions, wouldn't we notice? My electrons suddenly vanish.
That is the crucial question. And no, they aren't vanishing. The math shows they are extending. They stretch out into the fifth dimension.
Extending.
And by doing that, by existing across this bigger 5D bulk, they gain what the researchers call bulk masses.
And these bulk masses appear in a place they've named the dark sector.
Correct. The dark sector is basically a pocket within that warped fifth dimension. And these dimension-traveling fermions existing in that space are the dark matter.
So they're dark because they aren't fully on our brane, on our slice of reality.
Precisely. The electromagnetic force, the force of light, is stuck on our brain. Since these particles exist mostly outside of it, they don't interact with light. They're invisible to us.
But they do interact with gravity.
Yes, because gravity is the one force that works across the whole five-dimensional space. So they have gravitational pull, which is what we see holding galaxies together, but we can't detect them with any light-based telescope.
So the theory calls them fermionic dark matter relics.
That's the term, yes. It's an incredible mechanism. It uses particles we already know exist from the standard model, but just places them in a new geometry.
So if I'm getting this right, the reason we can't find dark matter isn't because it's some new, exotic, super rare particle. It's just normal matter hanging out in a five-dimensional pocket just next door, so to speak.
That's the essence of it, which of course leads to the most important question of all.
How do we prove it?
Exactly. That has always been the holdup for dark matter theories. They can be mathematically beautiful, but if you can't test it.
Well, according to the study, the path to proving it might be surprisingly straightforward. They say it would just require the right kind of gravitational wave detector.
And that's the really exciting part. The idea is that the warping of space-time and the movement of mass between our 4D brane and the 5D bulk would create unique ripples in space-time.
Gravitational waves.
Unique gravitational waves. A signature that's different from, say, two black holes colliding. And the technology to find these subtle waves is getting better and better.
We have detectors all over the world coming online.
We do. Next-generation projects that are looking for exactly these kinds of faint background signals.
Yeah.
So the answer could.
Yeah.
It could literally be lurking just around the corner.
It's incredible. So to sum this all up for everyone listening, dark matter is a huge problem. The standard model can't solve it, and the model has its own structural issue, the hierarchy problem.
Right.
This new research suggests a warped fifth dimension solves both. It uses quantum portals to send normal particles, fermions, into a dark sector.
Where they get a bulk mass.
And that bulk mass is what we feel as dark matter. It's invisible to us because it's not really playing with light, but it is playing with gravity.
A perfect summary. So, what does this all mean?
That's the final thought.
If, and it's still a big if, but if a gravitational wave detector picks up this specific signature, it would be the biggest discovery in physics since the Higgs boson.
It wouldn't just be finding dark matter.
Not at all. It would be observational proof of another dimension. It would completely reshape our fundamental understanding of reality itself.
A truly mind-bending possibility. And a perfect place to end this deep dive. We really encourage you to look at the source material we talked about. Keep that journey of knowledge going.
Absolutely.
And thank you again for joining us, curious learners. Don't forget to like, subscribe, and tell us what deep cosmic mystery we should get into next time. We'll catch you on the next deep dive.